2 conceptual questions, and then I want to just talk about, I just want to wrap things up. So I want to look at 2 conceptual questions. And you should be thinking about this when you answer energy questions from the for the exam as well as the final. Always think about bar diagrams because it's the way to identify energies. So what I need to do here is that I need to set up a situation. So the first one that we want to do here is that you're going to have, so in the first question, we're going to have a person swings from a rope and falls into water. So let's draw that picture. So what I imagine is that I have probably some grassy knoll, and I could imagine that this is something like this. So there's a person standing right here, and then down below is water. So I imagine that right here, I have water, and out of the water is a tree growing. So I imagine that I have a tree that's sort of like, something like this. And so now I have a tree. So now what I have here is that I have a person that's standing on top of this thing. So maybe this person's like right here. And what we know here is that this person is holding on to a rope. So I imagine that the rope is attached to the tree right here. Now what's going to happen here is that if that's the rope, what we want to look at is what is this person going to do? He's going to swing down. And so if I look at the path of the rope is going to go in an arc like this. And by the way, the tree is in the background. And we're going to look at 2 spots here. One spot is effectively right here. And I'm going to call this spot number 1. And then there's a second spot right here, which I'm going to call spot 2. And you're going to see that at this point, this person is going to release the rope and they're going to continue to go along that direction. And I'm going to say that this is path A. And then here, they're going to release at point 2, and then they will continue to go up and then fall in there. And then this is path B. So then lies the question. Which path leads to a higher speed upon entering the water? Okay. Which path will give you the highest speed in entering the water? So what I want to do here is that I want to copy this, and I want to bring it down here, and then I want to, because I want to use this as helping me with the bar diagram, but for right now, I want to come back over here. So the first thing that we want to do is we have to choose our system. Okay, So the first question, maybe I should bring this down. Maybe I should bring this over here just to spread things out a little bit better. So our first step is that we have to choose our system. So what is your system? Well, I do know that I have the force of gravity and I have the tension. So what am I going to do? I want Earth to be in my system. So then that means that I have a system that does this now. So when I look at my system, I am choosing the force of gravity to be part of the system, which then means that its work can be converted into potential energy. Now, there is another force, which is the tension force of the rope. So let's go look at that. So our system equals the person plus the Earth. So are there any external forces? Yes. What's the external force? It's the tension force of the rope. So what do I know about that? Look at the swing now. So if you're looking at the swing, here's what you're seeing. So as you swing, the tension force is always going to be perpendicular to the displacement. In other words, I'm going to have a tension force, in other words, a centripetal force that's always moving or changing direction so that it points towards the center of the circle. However, there's the path. So what's the path in this situation? The displacement is always perpendicular to the tension force. And what we know here is that when I look at this thing, I could then say that when I look at the work, the net work, I see that there's this tension force, but that guy is perpendicular. And because it's perpendicular to the displacement, it will always be zero. And because it's always equal to zero, then this force of gravity will change the kinetic energy, or I could then write this as that the mechanical energy in this situation is a constant. So I can use conservation of mechanical energy since the force of gravity is part of the system. That being the case, now let's use a bar diagram. Okay, let's use a bar diagram. So if I use a bar diagram, let me set this, the water level at one of these lines. Then you're seeing here is that this is the level right there. And this is the point where I'm going to choose y equal to 0. So when I look at the person, what do I see about this person? So if I call that point 1 and I call that point 2, I'm going to call this point 0. Now, in order for him or her to get off the top of the hill, they need a tiny bit of kinetic energy. Unless they can just sort of like, well, they got a step. You need a little bit of tiny kinetic energy. So here I go. Let's look at the kinetic energies. So if I look at the kinetic energy, what I see here, excuse me, not the kinetic, but the potential energy, this is the gravitational potential energy because that's the height of that person above them. Now, in order to get off that hill, you need a tiny bit of kinetic energy. So now I'm set. This is my constant. All of the energies have to readjust themselves in order to keep conservation of energy fixed. So this is state equal to 0. So now look at path A. When you take path A, what you see here is that when they reach the bottom, the gravitational potential energy right here, that potential energy at point A or point 0, not point 0, point 1 is 0. In other words, the rest of it has to be kinetic energy. When I look at path B, when I get to here, that gravitational potential energy from that path, B, has to be 0 as well. Conservation of energy then forces us to immediately state that the rest of the energy must be the same. So there's only one conclusion we can say then. Since both paths end with the same kinetic energies, in other words, K1 is the same as K2, they both enter the water with the same speeds. In other words, V1 is the same as V2. Now note, this is an extremely difficult problem if you try to use Newton's laws. You would really have to work yourself pretty damn hard to get this answer. Okay, let me look at another one, which I think is really good. And this is part of the energy PLC that you didn't have to turn in. And this is, oh, no, that's not what I want. Here, let me go get this other one. I'm going to paste this. And this is one of the questions from one of the energy PLCs. And this is a really good question. And it's an easy one to get incorrect. Now, one of the things that we want to look at here is that you have 3 balls that are fired simultaneously at equal speeds from the same height from the ground. So we see here that we have three paths, 1, 2, and 3. Okay, so this guy is literally 2 here. So let's try to set this up. We kind of had this already, so let's kind of set this picture up. So I imagine that we have some cliff, right? That we can look at that. And so when you're looking at the cliff, we're going to maybe have some type of platform that we can actually shoot these balls from. And so the first thing that I'll do here is that for 1, 2, and 3, I'm going to color these balls different colors to identify them. So the first one, which is going to be ball number 1, the second one will be this orange one, and let's say that this third one is going to be this guy. So this guy is going to be 2, 3, and now we know their speeds. So this one is shot up, this one is shot straight down, and then this one is shot horizontally. So all we know is that I'm going to look at these initial speeds, and the initial speeds tell us that all 3 balls have the same initial speeds. In other words, V1 of 0, V2 of 0, and V3 of 0 are equal. So now that we have that, we need to choose our system. So what am I going to do? Well, I would say that we definitely see that the only force that's going to be acting on them is the force of gravity. So I want to include the force of gravity. Now, you know what? I want to copy this before I get too deep into it. Okay. So if I look at my system, I have the force of gravity here. And so I could come in here and I could pick all of these to have Earth as part of the system. So therefore, the force of gravity is an internal force. So now, here's the thing. And this is really hard to comprehend. Kinetic energy is independent of angle and only depends on the speed. That's pretty hard to believe. And let me show you why that might be the case. So suppose we have a velocity vector. So if we have a velocity vector, then the magnitude of the velocity is going to be Vx squared plus Vy squared. And if I shoot this velocity at an angle, this will then be V cosine of theta squared plus V sine of theta squared square root. So picture-wise, I'm actually taking a vector, a velocity vector like this, and then I'm going to create an x component, with this as being the angle here, and I'm going to create a y component that looks like that. That's what this means. So now, look what happens. I can factor out v squared. So I'm going to get v squared, and I'm going to get cosine squared of theta plus sine squared of theta square root. But this is this relationship right here. Cosine squared plus sine squared is equal to 1, which then means that this is the square root of v squared which is equal to V. In other words, you know what? I actually made a mistake. I should have squared this. I do not want the square root. That was my error. Because kinetic energy does not have a square. I mean, it does. It's not by itself. So what I'm trying to show you here is that when I look at velocity squared and its components, you could see here that the final result here, that this is independent of angle. In other words, kinetic energy only depends on speed, and it doesn't matter about the angle. So now, let's put this picture back into here. So here's what we do. I'm going to draw a bar diagram. You could see that each of these, if I set my ground equal to 0 here, they all start off at the same height. So if this is my ground level, then you could see that these guys have this amount of potential energy for UG1. So now I can copy these because they all have the same height. So the only thing that I'm going to do different here is that I'm going to come in and I'm going to change this to 2 and 3. Now, because kinetic energy only depends on speed, that tells me is that each of these must have the same kinetic energy because they were launched with the same speed. So in other words, each of these guys has exactly the same kinetic energy. In other words, each of these balls has the same constant mechanical energy. So now if I look at when it reaches the bottom, we can see here at the bottom here tells me that the final gravitational potential is 0. Therefore, each of these balls must have the same final kinetic energy. In other words, each ball ends with the same kinetic energy, and therefore their speeds are the same. In other words, V1 final, V2 final, and V3 final are all the same, and they hit the ground with the same speed. That's how I would use bar diagrams to look at, conceptual questions. They're extremely, extremely powerful. Okay, I want to stop here and I want to say a couple of words here. A couple of things that I want to say here is that you signed up for a course that was face-to-face, not an online course. And I truly apologize for that. Little did I know that this was going to happen to my knee, before school started. So the fact is that I went through COVID teaching, and I know exactly what happened during COVID. Students struggled a lot because they had a paradigm shift in how people had to learn. As a consequence, I am going to look at grading as if it was during COVID period. It's a different scenario than face-to-face teaching. So when I do my grading for the exams, as well as turning in grades, I'm going to treat this in a very similar way that I did to COVID. So the grading is going to be different. Do I wish that things were different? Of course I do. If I knew that my knee was going to be in this situation, I would have taken a leave of absence and not taught this semester. But that's not the way it is. So one of the things that I want to say here is that I want to thank you. I'm sure it's been frustrating. I know that typically I'm very in tune with dates and setting things up, but my mind was on my knee, and that's why I said I should not have taught this semester. But I tried to give it the best shot that I had under the circumstances, and I know that next semester I will be teaching face-to-face the whole semester. And so maybe I might see you in the PLC, maybe I won't. But either way, I want to thank you for taking the class, and good luck to you on these exams, and hopefully everything turns out well for you. Okay, thank you. I'll post this stuff in a little bit, and I'll be around in office hours. I hate teaching online, and having office hours online is also terrible because I'm typically here by myself. And I want to thank Angie for showing up because that was very useful to me. And just so you know. Okay, thanks a lot, and good luck on the exam. Remember, it's due midnight on Friday. Okay, bye.